Before we go on to constructing relativistic physics, there's another important consequence of Lorentz invariance, another important way it teaches us to look at the universe that we need to come back to, and we need to understand this thing called the invariant interval. So, these are our Lorentz transformations. When you study them, you notice that they have the following exciting property, that if you compute this combination of t and x, c squared times t squared minus x squared, in one frame, or compute c squared times t squared minus x squared in the other frame, you get the same answer. This is why it's called the invariant interval. All observers agree on it. Now, this turns out that to have great physical significance, in fact, you can derive much of relativity from just this property. Notice that there are, this breaks up the universe into three pieces when you have a particular event. So I'm going to pick a particular event to be x equals t equals 0. That's right here and now. And remember that we are talking about now over here and here all up and down this axis. And what I notice is, first of all, if I set s equal to 0, that means that c times t is either plus or minus x. Oh, x is either plus or minus c times t. That means these two trajectories of beams of light going either to the right or to the left, emerging from the event that we called x equals t equals 0, or any particular event. Or, by the way, if you go to negative t, beams of light coming from the left or from the right and impinging exactly at t equals 0, at x equals 0. All of these are the regions in space at which s squared is 0, and of course it's 0, and we said that these light world lines are preserved in both, in any frame, so it's not surprising that s equals 0 in one frame means s equals 0. In the other frame, these two lines are called the light cone, and they kind of look funny for a cone, but you can imagine that they would be an actual cone if space were not one-dimensional but two-dimensional. Then instead of minus x squared here, I would have to add minus y squared minus z squared, and here minus y prime squared minus z prime squared. And if I only had y and not z, then x squared plus y squared equals some constant times t squared is a cone, so that the cone would be rotated this way in the, if you had a y-axis coming out of the board. If you have z, then this circle should be replaced by a sphere. That's drawing in more dimensions than I even care to attempt. So this is what is called the light cone, and light cones are very important. They describe for us, as I said, the trajectories of beams of light that cross at some particular event, moving in all possible directions. In one dimension, they either move to the left or to the right. Here, s squared is 0 along the light cone. The rest of the universe is divided into four regions in this two-dimensional case, though remember that if the light cone, if we were in a higher dimension, let me return those circles, then there are actually only three regions, because you can move around over here to connect. The entire outside of the light cone is connected, but the inside of the light cone always breaks up into two pieces. The inside of the light cone is the region where c squared t squared is bigger than x squared, and then either t is positive or negative. So there's a piece of the light cone here and a piece of the light cone there. Whereas the rest of the universe is where x squared is bigger than c squared t squared. So s squared is negative. This is negative. And s squared negative in more than two dimensions is one big region. Okay, what do these mean? Well, let's think about it. So what it means is this. Let's look at a region where s squared is positive. Remembering that s squared is c squared t squared minus x squared. This means that if I put some event over here at positive t, since ct is bigger than x, now I'm making everything positive so I can take the square roots, that means that x over t is less than the speed of light, c. So I can construct an observer. I can throw a rock or construct an observer that starts at this event and ends up here. This is an allowed motion for an observer because all world lines of observers are, remember, constrained by v less than c to be within this region. Oh, so that means two things. One is, it means that if I want to, say, cause something to happen here, I can do it by throwing a rock at it. If I throw the rock, I might need to throw the rock very fast, but it doesn't need to go faster than light. The other thing is, if instead of throwing a rock, I throw a clock, then I've essentially established a t-prime axis, which goes through both this event and that event. There is some observer that is present at both. In that frame, I can now draw the corresponding x-prime axis if I want. But the important thing is that in that frame, the two events happened at exactly the same place. They happened exactly at the same place. That means they both happened along the t-prime axis at x prime equals 0. And so s squared is actually c squared times t prime squared, where t prime is the length of time as measured by the clock I threw there. This is what we call proper time. It's the time between these two events as measured by a clock that is inertial and is present at both events. And this is given in terms of the invariant interval, which must be positive for there to exist such a clock, as the root of s squared divided by c. We call that proper time and often denote it by the Greek letter tau. Correspondingly, if I have an event down here at negative t with s squared positive, then that negative t is still bigger in magnitude than x squared, and that again, you can just follow this down here. That means the event is sitting inside the light cone, and an observer from there, moving at less than the speed of light, can make it to x equals t equals 0, and therefore you could throw a rock from here and hit somebody there, and again, the time as measured by that rock, if it were a clock, would be the proper time. So we have fancy names for these two parts of the light cone, and they indicate their significance. The upper part of the light cone with t bigger than 0 and s squared positive is called the future. It's called the future because these are all the places where I can throw something at less than the speed of light, and if you include the boundary, which is all the events that can be reached at the speed of light from my current location, and if you remember that nothing moves faster than light, then all of the events here are all of the events on which a decision taken here could possibly have an influence. I can decide whether or not to throw a rock that would hit here. I have no way to make a rock get to here. So whether this is my future or my past doesn't matter. It's not my causal future because no physical influence will be allowed. I cannot throw a rock faster than light, so I cannot make a rock that was here also be present at this position at that time. That requires moving faster than light. Similarly, this part over here is legitimately my causal past. These are all the events where someone taking a decision there could still get the information or the causal effect to me at this position x equals t equals 0. So every event in space-time, every point in this four-dimensional thing has a light cone associated to it, which breaks the space-time into three regions: the future, the past, and the rest. And remember, these are actually connected, so there are really three regions rather than four. What's the rest? Well, let's see what the rest is. If s squared is negative, that means you're outside the light cone. Well, for one thing, we said no observer can get from here to there. So we're talking now about an event over here. I can't have an observer for which this is on the t-axis, because that observer's t-axis would be tilting more than 45 degrees from the vertical. But for that reason, of course, I can find an observer for which this event lies on his x-prime axis. That means I can't make it fall at the same position as I did before for some observer as x equals 0, but I can make it simultaneous. So I can always find some observer for any event here in the outside of the light cone. There is some observer who thinks it's on the x-prime axis, who think it's simultaneous with the event we started with. For that observer, of course, the time of this event is t prime equals 0. Here's the speed with which that observer needs to move, and because t squared is bigger than x squared, then c squared, t squared is bigger than x squared. This is less than the speed of light, so that's legitimate. And that means that for that observer, since t prime is 0, s squared is just negative x prime squared, so the root of negative s squared, when this makes sense, when s squared is negative, is the proper distance. It's the distance between these two events as seen but measured by the observer for which they are simultaneous, of which that determines the speed with which that observer moves. And now, what happens if instead of this green observer, I consider an observer moving even faster? So his world line tilts from the vertical even more than that of the green observer. And his x double prime axis tilts from the horizontal even more. So for that observer, notice this point here, which had a positive value of t, has a negative value of t double prime. The black observer thinks this event happened after the exciting meeting of all the observers over here. The green observer thinks it happened at the same time, and the blue observer thinks it happened before they met. So it's a darned good thing that no decision taken here could impact something that happened there, because if it could, then the blue observer would think that effect preceded cause. You can only maintain, in the context of this crazy relative simultaneity story, the construct of a causal theory if you allow that no material particle, we already talked about that, no observer, but also no information, no physical effect can move faster than light, because moving faster than light is precisely tantamount to moving in an acausal way to effect preceding cause, as long as you allow for its effect preceding cause as seen by someone moving sufficiently fast in the appropriate direction. The result is that we cannot allow in a relativistic theory any information to propagate faster than light. This is the origin of the idea of a cosmic speed limit, the speed of light, not only on material particles, but also on information.